All right, let's pick up where we left off last time. 101 plus projectile problems. The key is, of course, go through your process, read the problem. You know your tools, constant acceleration equations for projectiles in the horizontal direction and vertical. Choose whether you want plus to be up or down to be, plus to be down. Either way is fine. Just be consistent. If I see something going up, then I choose plus up. So I use this coordinate system. We're looking at the key, the vectors in the problem. Of course, it's acceleration, which we know is down the entire time with a value of g. And then we've got velocity vectors. So the velocity itself, the total velocity, is tangent to the path v1, v2, v3, v4, v5, v6. And of course, it dives down like any projectile does. And you just throw something and you'll see. In reality, air resistance, if you throw a cotton ball, it doesn't work too well. So what we're looking at is multiple times, any states or moments or instants or events, however you want to call it. And we can relate any earlier state to any later state through our equations. And then we just rewrite the equations for in two other states. Of course, the time, delta t from 1 to 2, is the same in the x direction as the y, because it's doing both motions at the same time. So the delta t's in the x component equations and the delta t in the y component equations are, of course, the same. You just have to be clear which time, 1 to 2, 2 to 3, 1 to 3, whatever it is. Okay, that said, now let's get some meat. Here's a couple of good stuff. One thing, I know that the velocity in the x direction is the same because the acceleration is 0. So if I look at this picture and I look at this, I should be able to see something. We're increasing our awareness now of this motion. One thing I should see is that there's my delta x 1 to 2. Here's my delta x 2 to 3. Here's my delta x 3 to 4. Those are different delta x's. And so from that picture, if it's right, if it's not just a sketch, from that picture, I'd say that the time is longer 1 to 2, a little shorter 2 to 3, even shorter 3 to 4, if that picture is scaled correctly. Okay? So you don't necessarily have to take snapshots in equal intervals of time, wherever you're interested in looking at it. A split second after it reaches the top, a tenth of a second, whatever, 0.15 seconds, whatever you want, anywhere you want. Okay, so notice time by looking at the x displacement, delta x. That's one thing. The other thing that you should notice here, we were talking about velocity components. Again, Vx being constant, giving you a clue to the time. Vy, as you know, you decrease speed on the way up. You stop only for a moment. You don't stop and hover. And then you increase speed, or the object increases speed downward, always with a downward g. So what does that tell you? That tells you that if up is positive, 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 0, negative, 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 and more negative. There's more, though. What that tells you here, building on what we said, is if I look at these two states, which are rather useful states to look at, this one, and then over here at the same level, this one, what I know is delta y is, well, I called it 1 to 5. Delta y 1 to 5, we said, is 0. Now, it doesn't mean it stops. It could be just before it hits the ground, or it might keep going. It doesn't matter. Absolutely doesn't matter. For delta y from here to here is 0. Now, let's see. What does that tell me? What does that tell me about the velocity v5y? Well, one way you can get this, and it's good to get this two ways, intuitively and through the math. So the math down here, if I look at the equation, and if I'm going 1 to 5, so let me go here. V later is 5. V earlier is 1. Delta y is 1 to 5. Remember, making it specific. Hold on, we love zeros in this case. And that tells me V5 y component squared equals V1 y component squared. That tells me that V5y is negative V1y, because clearly I'm going the opposite direction. And so that's another piece of implied information, since delta y, 1 to 5, is 0. So often in problems, key places are top, same height as released, coming back down. And that's true if you throw it straight up too. When it comes back down to the same height, whatever it was, if it's going up, it doesn't matter. You can release it here, slowing down, faster here, slowing down here, comes back down. It's going to be going the same speed in the opposite direction, same speed in the opposite direction if it's the same height. How do I prove that? Well, between here and here, delta y is 0, and the velocity squares are equal to the opposite direction. So that's cool information. Keep that in mind. Always, you just have to be aware of your Vx and your Vy. And know that. Put it down, put what's implied. Vy at top is 0, etc. And you're good to go. Notice your delta x as your displacements between any two states. Notice your delta y's as displacements. And keep in mind, it's critical that you're just looking from wherever you start, whatever your earlier is, to your later. It doesn't matter how you get it. Here up to here. Here up to here. Here down to here. Or if I start here to here, then that's my delta y from 1, 2, 3, 4 to 6. That's my delta y. So just see it. And that's deeper than you might think in a lot of more advanced problems. If you use your picture and you look at each of these variables in our general form of the equations, they will guide you, and the algebra will come out often nice. Other thing to notice, from 1 to 5, delta y is 0. So I got rid of that. And again, if I go 1 to 5, that's 0. Doesn't go away. I got 0 is equal to V1y. I don't know. Some of it I know, some of it I don't. I'm not worrying about that. The time from 1 to 5, the time from 1 to 5. And so let's take a look at that particular case. Okay, again, this is called, delta x is called the range often. So it's the range equation, which you should absolutely be able to derive. I wouldn't memorize unless it was my job what that is. So let's try that out. And then we'll look at more specific problems. But you don't want to memorize solutions. You want to memorize a general plan and go in and be able to take any variation on an exam and be able to lay it down. Just quickly, don't worry about how it's going to come out. Quickly lay out your information. I'm going to go like this. I'm going to go, okay, I'm going to shoot it up at some whatever angle. It doesn't matter. Theta 1, V1. And maybe I don't care about the top, but often I do. I'm just going to throw that state in there just in case someone asks me something about it. And I'm going to go over here. And maybe it keeps going, maybe not. There's something very interesting here. Okay, V3, right there. All right. So, let's take a look. I want to go 1 to 3. So, what do? I say, okay, I want to go 1 to 3. Write it. 1 to 3. Delta x, 1 to 3, is equal to Vx, which is always the same, so I don't have to worry about it. Delta t, 1 to 3. And then I've got delta y. So write it quickly, quickly. The faster you write it, the clearer you are and more solid you feel. Delta y 1 to 3 is equal to v1y, delta t 1 to 3. I'm going to call plus upward. That's plus y, so ay is equal to negative g negative 1/2 g delta t 1 to 3 squared. Cool. And this is it. I'm doing the physics now. Algebra is not the physics. It's part of it. We need it. But V3y, don't just put V3. It's only the y part. V3y is equal to V1y minus g delta t 1 to 3. Or I can do algebra and solve and get this equation. So I'm just going to quick look how fast you can write this. Once you decide you're going 1 to 3, you're cool. And then you go like this and you go, hey, wait a minute, what do I know? I don't know. I want to know. This is maybe my equation. What's that? The so-called range when I get back to the same height. How far can I throw it? Assuming when I throw it, someone catches it at the same height, say. And then I've got this stuff. I don't know. Let's go over here. Oh, wait. Clearly, I'm thinking in terms of x and y v's and x and y displacements. That's 0. That's 0. So the whole thing goes away. This just tells me that v3y is equal to negative v1y. The math doesn't tell me the negative. The physics does. Okay? You have to look at that. So fine. You know that. So no one has to tell you. Your job is to pull out the implied information. What else do I know? Well, since that's true, I could go here. I could do a number of things. Let's get rid of this, since you know this very well. Let's do a little math now. Let's take this, and now I'm going to go into that solve mode. So I've got 0 is equal to v1y delta t 1 to 3 minus 1/2 g delta t 1 to 3 squared. That's interesting. I can factor out that delta t. This is 0, so that's v1y minus 1/2 g delta t 1 to 3 square. Oops, hello. Factored it out, didn't I? Delta t 1 to 3. I'm just doing algebra now. Now, if 0 is equal to a times b, either a equals 0, or b equals 0, or a equals b equals 0. Maybe they're both 0. If delta t is 0, then I didn't really have two states. So that's not true. So this logic says that this part must equal, minus 1/2 g delta t 1 to 3. That must be 0. So now I couldn't memorize that. I just worked from the basics, and there I go. So, what am I doing? I'm looking for delta x. Well, I might need that time. So let's pull that out. Let's see the time here. That's 1/2 g delta t 1 to 3. Pull it over here so it's plus, is equal to v1y. You can do the algebra. I'll leave that to you. It's better for you. That's delta t 1 to 3 is equal to 2 v1y over g. It's not squared. Remember what happened to the square thing. It got pulled out. Fine. Doesn't matter. Just do your algebra. Don't have to memorize this. And that looks good to me, unless I made a mistake. Right? Now I'm going to go ahead and say, hey, v1y, that's, in this case, up, so it's positive v1 sine theta 1 over g. All right, cool. So I've got that. That's what all that turned into. And now I want to know delta x. Well, that's Vx, which is the same anywhere. Maybe I've got V1 cosine theta 1. That's what this guy is. And my delta t, hey, that's this guy. So it's too much to memorize, but I'm just going by the steps. I know what I want. Sine theta 1 over g. All right, cool. Let's see. So the range, that is if it lands at the same height as the released, or doesn't have to land, delta x 1 to 3, sometimes called r, but I called it 1 to 3. It doesn't have to be. It could be 1 to 2. Is equal to 2 V1 squared cos theta 1 sine theta 1 divided by g. Kind of like to put the numbers out here, and we've got it like that. All right, so that's an interesting result. And it just came from one step at a time. Draw your picture, use your method, it's always the same in this case, and then put in what you've got and take it and see where it takes you. You're always going to get this as the range, but don't memorize it. Don't shortcut. Shortcuts means you're going to end up being weak. So, let's see, where do we go from here? All right, there's my picture. How can I explore the meaning of this? All right, I know delta y is 0 because that's what I've implied. I've got this range equation. Right, so that's kind of interesting. I don't have to memorize those steps. I just know where to start. Take it from there. Don't memorize it. That'll slow you down. Be familiar with it. Do it a bunch. And then just go and do it. If you work from memory, it's no good. Okay. So what does this tell me? Well, clearly, if I shoot it faster, I'll go farther. Whoopee. You know. But what if I just assume, you know, I shoot at whatever speed or throw it at whatever speed I can? So V1 is some set value. Then how can I affect where it lands? Well, I can change, the only other thing that I can change in this equation is the angle. All right, cool. So let's look at this. Now here's a neat thing about complementary angles. So this is where I'm analyzing my result. Now you're doing a lot and you're taking a lot of classes and this is all coming at you fast. So you may not realize this right away, so here's a little lesson. If I look at complementary angles like, let's say 10 degrees and 80 degrees. Or I can look at 20 degrees and 70 degrees, or 30 and 60, or anything you want, 25 degrees and 65 degrees, or 26 degrees and 64 degrees, right? So whatever you've got, the nice thing is that the cosine of this angle, let's call it alpha, is equal to the sine of this angle. Let's call it beta. Doesn't matter what you call it, right? All right. So that's interesting. Cosine of alpha equals the sine of beta. So what does that tell us? If I shoot it at any of these angles, what I've got is, I'm going to call these alpha, I'm going to call these beta. I've got delta x. I'm going to keep my 1 to 3, it doesn't matter, is equal to 2 v1 squared over g, nothing's changing there, times cosine of alpha, and it's still the same, sine of alpha. I'm shooting at one of these angles less than 45 degrees. But that's interesting because that's also equal to, follow this, 2 v1 squared over g. If I shot it at one of these complementary angles, well, cosine of alpha is the same as sine of beta, and sine of alpha is the same as cosine, complementary sine of the complementary angle. So that means that that product is the same whether I use the angle less than 45 or the complementary angle greater than 45, which means it'll land in the same place, which is way cool. And so the picture there is this. How we doing?